Hey guys, my name's Ian. I'm joined by Nina, Kara, and Ananya, and we are the UASB or Upflow Anaerobic Sludge Blanket team. So, UASB is part of Agua working on the wastewater side of things. So, if you go to the next slide, please. We are working on kind of a new side of Agua Clara that's doing wastewater treatment. So what is wastewater treatment? You might be wondering. Basically, wastewater is defined as any water that's used for some application and then is dirty and has to be cleaned first. So that includes stuff from your toilet, which is what you might conventionally think about, as well as anything from your sinks, showers, laundry, anything like that. So once that water comes out of your house, generally it's dirty. It'll go through some sort of wastewater treatment plant or process that will remove all the contaminants from it, and then the clean water is released back into the environment. So, why is this important? Why is it important to treat wastewater? Directly discharging wastewater without treating it is really, really bad for a number of reasons. One is for human health, a bunch of really serious waterborne diseases are spread through wastewater and human waste. So stuff like salmonella and cholera can be released direct to the environment, get into waterways, and then if someone uses that water as drinking water later, they can get infected. It also has a lot of other contaminants that can cause these huge algae blooms, and that can really damage kind of the environment because it will remove all the oxygen from these lakes, rivers, and actually kill all the wildlife there. So what we are kind of trying to do to create a new wastewater treatment process is using the UASB reactor. So you might be wondering, what exactly is a UASB reactor? So you can essentially picture it as basically a large cylindrical tank that water flows through and is treated in. So as you can see here, water flows in through the bottom and goes up, hence the upflow. And as it goes up through there, it passes through this sludge blanket right here. The sludge blanket is basically a giant conglomeration of all these different bacteria and these things called granules. So picture just small little clusters of just gross bacteria everywhere. So as the wastewater flows through the sludge blanket, these bacteria will actually take some of the organic contaminants in the wastewater and eat them essentially as their metabolic food source. And in the process of doing that, they remove the contaminants from the water, which is good, and that helps everyone. And then clean water comes out through the top. A nice benefit of the sludge blanket as well is because these bacteria are all anaerobic, they don't use oxygen. They produce biogas, which is kind of a mixture of methane and CO2. And this just rises up and can be collected in the top. This is really helpful because biogas has a lot of energy in it, like methane, is something we use for heating. So by burning that, you can create energy or do some heating. So UASBs are kind of a conventional system that is already being used, but what we're working on is actually kind of innovating on that design to do something new. So following kind of the Agua Clara mantra, we are designing a completely gravity-powered system. So no electrical inputs, no mechanical inputs at all. Everything is driven by differences in elevation of the water coming in and going out. So this is really good because then you don't need to rely on the electrical source, and it's much more accessible in different parts of the world that may not have electricity available at all times. It's also at a much smaller scale. So the reactor we're designing right now is about 7 feet tall and about 3 feet wide. So this is much easier to be built quickly and easily and much cheaper as well, and can also be implemented easier in kind of our target communities, which are smaller rural areas that don't have access to wastewater treatment. And then finally, we kind of go for a simple use and easy fabrication model. So basically designing it to be cheap and easy to build so we can build a lot of them very quickly. Yeah, now Kara will tell you about some of our designs.
So the main problem we have been working on this semester is getting the velocity of the water coming in through the inlet correct. So basically it's kind of a tricky thing, because if the water that's coming in here is at too high of a velocity, it's going to wash the sludge granules out, and obviously that's not what we want. But if the velocity is too low, then it's not really going to properly fluidize the bed, and then it's not going to get treated either. So we kind of have to find a middle ground. So this is where our tipping bucket comes in. So keeping with, like Ian said, an electricity-free system, water will just flow through the tipping bucket until it reaches a certain weight. Bucket will tip over, pour the water down, and that way it creates a nice pulse of water to properly fluidize the bed. So to test this out, we have been doing our tapioca test all this semester. So as you can see, we have this pump right here, which is kindly borrowed from our friends at CDARC. So water comes in the inlet tube, all the way down, and then it flows up. So, and then once it is gone all the way to the top, it goes out the effluent pipe. So we have been doing, so to test to see how the water is flowing through the bed, we have been using some red dye. So as you can see from our little GIF, can't see too well, I don't think, but basically red dye is coming up here, and so we get to kind of see how the wastewater is moving through the bed. So we really wanted to just like go evenly through the bed, so all of the sludge granules can get contacted with the wastewater, and therefore maximizing wastewater treatment. But that's not really what's happening here. What's happening is the preferential pathways are forming, which is when the water makes like little gaps, and they just kind of flow through those gaps instead of actually like going through the entire bed, because the water is going to go through the path of least resistance. And so we were seeing this was not happening, but we kind of wanted to get a more quantitative sense of kind of what is going on, because you can't really see this too well. So that's where our photometer comes in. Nina?
Okay, yeah, so as Kara started telling you guys, this semester we decided to implement a photometer in our testing so that we can get quantitative data about how water is flowing through our model UASB reactor. So what we had to do first was calibrate the photometer, and you can see our calibration curve there. And then it's important to understand actually what the photometer will be measuring. So as Kara was describing earlier, with our tapioca tests, we inject a plug of red dye into the reactor, and then if the reactor is functioning properly, the red dye should flow up through the sludge blanket kind of together in one burst, and then come out in the effluent line in a concentration similar to the concentration that it was injected into the UASB reactor at. So there's our photometer, and that's generally what's going on with the photometer. So then, after we decided to use a photometer, we realized that tapioca was no longer a suitable option to use as a model for sludge granules, because tapioca, when it's in water, it leaves a big residue. It makes the water very cloudy, so the photometer is not able to measure the concentration of red dye in the water accurately. So upon coming to that realization, we decided that chia seeds might be a good material to model the sludge granules with, since they're also sharing similar material properties, but they don't give off that cloudy residue. Unfortunately, chia seeds are very sticky, and so they're not a great model either, we realized, because they stick to the walls of the reactor, and they stick to each other, which prevents water from flowing evenly through the granules, and it just doesn't really model what's going on. So then, after we realized that chia seeds also weren't a great option for modeling sludge granules, we did some research, and we came to the conclusion that glass beads that have a similar density to sludge granules would probably be our best option. So we didn't have time this semester to order the glass beads, but there were some glass marbles laying around in the lab, so we decided to use those as a model for the sludge granules. And it turned out that those were too heavy for the influent water to lift, so those also weren't a great model. But on the bright side, using the marbles was a good way to practice collecting data with the photometer. And another future plan for next semester is to hopefully get some real sludge granules so we can use those for testing. And one last thing, so I was just talking about kind of what's been going on this semester, but bringing back from a few semesters ago, the UASB team applied for Phase 2 funding from the EPA, and recently we found out that the funding will probably be approved, so that's really exciting because we can, order new glass beads and get materials for our pilot UASB reactor, which Ananya will talk about at the end of the presentation.
So this semester, the UASB team also presented our research at the Northeastern Graduate Students Water Symposium, or Nexus, in Amherst. And this was a really great opportunity for UASB to showcase its research in a poster to faculty and students from different universities in the country. and get the idea of what Agua Clara is doing, especially in wastewater, across to different people for possible collaborations. So this was a really great opportunity, and pictured here is me representing UASB with our research poster, and then on the other side, Oliver, who was presenting AIDS work too. So this was just generally an excellent outreach opportunity for Agua Clara. Transitioning to what the UASB team plans to do in the future, one of the most important decisions we made is to divide our team into 2 separate sub-teams next semester, and this was mainly inspired by the problems that we faced this semester in dividing our work evenly between benchtop testing and designing the reactor. So essentially, there will be a design team that will work on designing different components of the reactor, and a research team that will continue all the benchtop testing that we've been talking about this semester. So the design team's main focus is, as mentioned, to design and finalize all the different components of the UASB reactor, including the effluent tube and the biogas capture, and write code that will help us document it and run tests on it. Another responsibility will be to make a CAD model of our UASB reactor on Onshape, which will allow us to better document our design and modify parameters and receive visual results. Another important goal of the design team will be to design a pilot reactor for the UASB. And this pilot reactor will actually be tested in the Ithaca wastewater treatment plant. And this is a project that's been in the works for a couple of semesters now, and we've been in talks with the plant operator, Ed Gottlieb, who's very kindly provided us space within the facility to install a pilot UASB reactor and run municipal wastewater through it. And the advantage of such a test would be that the data that we get from this test will allow us to compare our reactor's performance against conventional wastewater treatment systems and improve our UASB design until it's ready to be fabricated and shipped to Honduras. The research team, on the other hand, will continue this semester's benchtop testings and basically work alongside the design team in determining optimal geometry and orientations and reactor performance on a lab scale that will better help us design a full-size UASB reactor. Thank you.